I'm going to go ahead and start on chapter 17. But first, I want to remind everybody, Thursday we're going to do, the lab is Ka of acetic acid, the one that we missed last Thursday. And then the week following that, we're going to do formation constant for complex ion. And then that will be the last lab. We're just going to throw out the last lab on electrochemistry. All right, and both of these, Ka of acetic acid and formation constant, are both formal labs. So you'll need to have your notebook set up for that. Let's see, ding-a-ling. Oh, okay, there's Jada. See anybody else? Oops, didn't mean to do that. All right, we can get started on chapter 17. Spontaneity, entropy, and free energy. This chapter is a continuation of previous discussions we've had concerning thermodynamics. The first introduction you had to thermodynamics, probably didn't realize it at the time, was thermochemistry. One of the labs we did where we were determining the heat of different reactions, heats of solution, acid-base neutralization, those things. That's your first introduction to thermodynamics. Just as a reminder, when we are looking at the progress of a chemical reaction, we go from reactants to products, and we've seen this before. We go through a transition state, which is higher energy. And once we get to the top and just barely over that peak, then the reactants can proceed to products. And the realm of kinetics that we've studied already occurs in the middle, where you see the activation energy is covered. And the domain of thermodynamics, and equilibrium is one of the topics that we've studied already. That thermodynamics or equilibrium is covered by reactants and products, and we don't really care what happens in between, which means that we may say something about equilibrium. You know, what are the concentrations of reactants and products at a point where the system is in equilibrium, but we say nothing about how fast it got there. All right. So by definition, oops, I lost my screen. Hold on a second. Big screen is rebooting, it looks like. That's fine. Had me scared for a minute. Okay, so trying to pick up where I left off. By definition, kinetics is dependent upon the path that's taken. In other words, we studied in kinetics that if the reaction proceeded through a certain number of elementary steps, that defined its path and also defined how fast the reaction would go. But if we introduced a catalyst, then we are introducing an alternate set of elementary steps. That gives you a different path for the reaction to proceed. And in fact, with a catalyst, it means the path is faster. So kinetics is what we call a path function. Whereas thermodynamics is a state function, which means all we need to know to say anything about thermodynamics is what is the state of the system at any one time. And in some cases, we need to know the state at the beginning, the state at the end. And then we can say something about thermodynamics. But we don't need to know the pathway that's taken. Okay. One topic that's of primary interest to chemists is whether or not a given reaction is spontaneous or not spontaneous. And by spontaneous, it's intuitively accurate to say that spontaneous simply means that if we put reactants together, the reaction will proceed. And it doesn't require any outside intervention. Now, the conditions that we establish for that spontaneous reaction may vary depending on the reaction and the conditions that we choose. But once we set those conditions and put the reactants together, the reaction will proceed to products. Now, we know from equilibrium that all of the reactants don't necessarily produce products. You will have a balance where there are some reactants and some products. But the reaction itself is spontaneous in the forward direction. What thermodynamics allows us to do is to predict the direction that the process will occur spontaneously, saying nothing about the rate of the reaction, only whether or not the reaction will proceed as written. Okay, so consider this scenario, and this is really a physical process, but physics and chemistry sort of they're close first cousins. If we have a 2.4 moles of gas contained in a 4-liter bulb, we have a 4-liter bulb here with 2.4 moles of gas. Okay, and it's connected at the temperature of 32 degrees. Okay, and it's connected by a valve to a 20-liter bulb. So this is a 4-liter bulb, and it's connected by a valve to a 20-liter bulb. Okay, only the 20-liter bulb is evacuated. This is a vacuum. Nothing there. Okay, what should happen when we open the valve? If I open this valve, you know what's going to happen. The gas is going to rush into that until we get a balance. We studied that when we looked at gases. All right, but what's the explanation? Right, we know that the gas is going to proceed to fill that vacuum until the pressures are equalized. But what's the driving force? We can't just say that the vacuum sucked the gas in here, or the excess pressure here forced the gas into the vacuum. That doesn't give us a complete picture of what's happening. So in order to describe situations like this that we can't explain in terms of what we know about chemical reactions, right? We know that some driving forces for chemical reactions are formation of a gas in a reaction, let's see, formation of a solid, right? Formation of water for acid bases. Those tend to be driving forces. But even those don't give us a complete explanation of why the reaction proceeds spontaneously. So we need to introduce some terms here before we can go any further. Right? First term is delta H. And we've been introduced to this one before. This is enthalpy. Right? When we were studying thermochemistry, we were introduced to the topic of enthalpy. Enthalpy is a potential for either releasing energy from a reaction or absorbing energy from the surroundings. And this is also equal to internal energy, which we're going to define in just a second. Internal energy plus pressure times the change in volume. Now, internal energy, to make our picture complete, internal energy is the sum total of all energy in the system. This is total energy of any kind. And we have to define what kinds are dominant, of course. But that says that the system contains this much energy, and we're not differentiating one energy from another. Unless we want to, we can say some of the energy is kinetic energy, some of it is potential energy. And we'll have to define those terms also. Q is heat flow. And the reason we say heat flow and not just heat is that the only way to measure Q is to measure movement of of heat from from the source to its destination. And we do that predominantly by measuring temperature change. So this heat flow is a measured quantity. W equals workflow. And that's a measurable quantity also, right? Do we do work on the system, or does the system do work on its surroundings? And think back to when I described the what we mean by system and surroundings. All right, we defined what the system is, and everything else is surroundings. I've got a slide coming up for that one too. Okay, so in our scenario where we have the 2.4 moles of gas in a 4-liter bulb, and the temperature is constant throughout this experiment. Temperature does not change. And we connect it to an evacuated bulb and open the valve. All right. What happens in terms of these values that we've presented? They're all equal to 0. So let's look at these in terms of what we know about their definitions. Right? Let's look at this one first. Heat flow. Was there any heat flowing here? No, because the temperature is constant. Right? So that means this one has to be equal to 0. And since delta H is the potential for heat derived from this definition, this one is also equal to 0. Okay? Which means that the combination of these two has to be zero. Well, if the volume is expanding, but the pressure is dropping, and we know that from Boyle's law, then, and the gas is not pushing against any resistance, that means there's no work being done. No work has been done because the gas isn't pushing against anything. We can't measure any work that's being done. So, and the entire system is maintained at a constant temperature. And with the pressure decreasing and the volume increasing, this is a wash also. So internal energy is also zero. So all these factors are zero. The reason we're making that point is that we cannot blame or attribute the spontaneity of this process to any one of these factors, right? We need a new factor. So there's your constant temperature explanation. There's no change in energy. There's no change in enthalpy. There's no change in heat. And there's no work being done. All right. Delta E. Oh, I left that one out, didn't I? Delta E is equal to Q plus W, which means any change in heat flow, any change in work being done will add up to internal energy. And if both of these are zero, then internal energy has to be zero also. That's a better explanation, I think. An itchy nose. Somebody must be talking about me. Okay. What's the driving force for this reaction? Well, it puzzled people for quite a while at the beginning of the well, it was toward the end of the 19th century, the beginning of the 20th century. And physicists in particular, and chemists alongside, some of them are actually both physicists and chemists, decided, and the work in thermodynamics was furious, especially toward the middle of the 19th century and the close of the century. And the only thing they could come up with was an immeasurable value, which they called entropy. That term, now people have been working on this for a few years, but the term itself was proposed by Clausius, Rudolf Clausius. And it's given the symbol S. Capital S is entropy. Okay. So what we're saying is, for this process that we described earlier, entropy is not zero. In fact, in order for this process to occur, entropy must be greater than zero. There's Rudolf Clausius. It's strange. You look at any picture in this time frame in the early, middle 19th century, they all look like they're mad. I haven't seen one with a smile. Not even my grandparents with their pictures being taken. I think it had to do with the state of photography of the time. In other words, the exposures had to be very long, several seconds. So they encouraged people just to have a blank face so it wouldn't blur the photograph. But it looks like they're angry all the time. All right. So what we're trying to show here in this slide is a difference between the two. One where you have a vacuum and then you open the valve and the vacuum is filled. So what do we notice about these two images is that the molecules are more spread out in the second image. They've got more space. And that is one definition. Your first introduction to entropy is best accomplished by saying the molecules are more spread out. They've got more room. We call that disorder. They're more disordered. Okay. So this driving force and what came out of thermodynamics and the introduction of entropy is that a change in entropy. In other words, that first picture has a certain entropy, an absolute value that's not measurable, but it's calculatable. And the second one has more entropy. So if we take the final minus the initial, we find that delta S, the change in entropy, is greater than 0. Right? We ratio them just like any other before and after. Well, actually, we subtract them. We don't ratio them. We subtract the former from the initial from the final. And we get a change in entropy that's greater than 0. And that, in layman's terms, is an increase in disorder. There's more space for the same number of molecules. Now, if delta S is less than 0, we get a decrease in disorder. And that can happen. But in order to do that, we would have to take the gas and squeeze it into a smaller volume. Now the gas molecules have less space. There's, by definition, an increase in order or a decrease in disorder. And one practical example of that is if you condense a gas like a water vapor, condense water vapor into liquid water. Now we know that the gas is going to, the molecules in the gas are going to occupy less space in the liquid. We have increased the order, decreased the disorder of water. Now, we know what we have to do to get there, right? We have to extract heat. We have to remove heat or internal energy from that gas in order to do that. This is true. The term disorder used for entropy is an oversimplification, but it's a useful introduction. We're going to get into the details in just a second. There we go. What actually happens when we're talking about entropy is this thermodynamic function actually describes the number of possible arrangements of the particles in the system. Right? So if you can have more possible arrangements, you have an increase in entropy. And that comes in our first example from the same number of molecules occupying more space. They've got more room, more elbow room, so to speak. So they have a larger number of possible arrangements for those molecules in that space. And the natural, the spontaneous process is one that proceeds towards those states that have higher probability of existing. So if the more disordered state is true for various arrangements of the molecules, then that is the most probable and will generate the spontaneous reaction. Okay, I've got an example here. What I'm trying to describe to you is the number of microstates. Now we've got a bulb with actually two bulbs attached by a tube. And one possible microstate is for molecules A, B, C, and D to be all on one side. So how many microstates can we derive for that situation? Only one. Okay. Or look at the bottom. All of them could be in the right-hand bulb. So how many possible microstates there? Just one. So we look at the second one from the top. If we move A into the right-hand bulb, that's one microstate. If we put A back and move B, that's another one, and do the same thing for C and D, we have four possible microstates in this case. So this is a more probable arrangement to have four microstates versus one microstate. But if we go to the situation where we can move two into the right-hand bulb at a time and leave two behind, then the possible arrangements there would be six. So that one, arrangement 3, is a more probable situation than either 2 or 1. And then we could go to the others where we move 3 into the right hand, leave 1 behind. So that only has 4 microstates, and we've already covered the last one. So the most probable arrangement of particles in this hypothetical is the middle one, where you have an even distribution of 2 particles on one side and 2 on the other. That gives you the highest number of microstates and the most probable situation. Okay, so let's see. Let's clear the board. All right. Now that we've introduced the concept of microstates as an explanation for our term entropy, there are 2 possibilities. We can describe entropy in terms of position. In other words, where are all the particles in the system? And that's the one we've introduced this concept of disorder first, and microstates first. If a gas expands into a vacuum, we know now that we have more possible microstates because there's more volume, right? So we can envision billions and billions of different possible microstates in a gas, whereas with a liquid, we're confined to a smaller volume, and the molecules can only slide past one another. So they're restricted in their volume with the same number of molecules as the gas. They're restricted in their volume to fewer microstates. And then if we cool the liquid down further, we can create the solid, where now the molecules cannot slide past one another. They're locked in position. So their number of microstates is limited to positional microstates. You're limited to virtually just 1. Okay, so the entropy for a gas is much greater than that for a liquid, and the liquid much greater than that for the solid. And this is positional entropy. Positional entropy. Energy entropy, and unfortunately your textbook doesn't cover this, but I think it's an important concept. Energy entropy looks at the system in terms of its internal energy. In other words, how much internal energy is there in the system? Q plus W. So if we have Q plus W equals our internal energy, then we can change that in terms of adding heat or removing heat from the system, or doing work on the system, or letting the system do work on its surroundings. And that will change its internal energy. If the internal energy changes, then we get a change in energy entropy. One way to think of this is in terms of, gas, liquid, and solid. Right? So if we have this gas, and we're going to go to a liquid, and we're going to go to a solid, then how much energy do the particles have in a gas compared to the others? Much, much greater energy, very high. So if we remove some of that energy, not only are we changing the positional entropy, but we're reducing the amount of energy. So now all they can do is slide past one another with a certain amount of energy. But if we lock it into a solid, we've locked those molecules into a crystal structure, or a position where they cannot move, except they can still vibrate. So they still have some energy entropy in the fact that they can vibrate. They can't move very much, but they can vibrate. So they still have some entropy, some energy entropy. So these things go together. We can look at a system in terms of its positional entropy and its energy entropy. Exothermic processes, where you have the system and the surroundings. Exothermic processes lose heat from the system. Right? Q is leaving the system, which makes it negative. And if that's the case, we increase on the outside in the surroundings, the change in entropy is greater than zero, whereas inside, the change in entropy is less than zero. Okay? Based upon energy, just purely energy. We don't have to change the volume. We don't have to change the number of particles. If it could still be a gas. Let's just say we keep it a gas, but we allow some heat to travel from the system to the surroundings. Now we've changed not the volume or the number of particles, we've changed the energy entropy for the system. It's decreased because we've lost some energy. But the surroundings are getting that energy, and now the surroundings have an increase in energy entropy. We can talk about in the opposite direction, where Q is positive. Now it would be the other way around, right? Instead of that one, we would decrease energy entropy for the surroundings and increase energy entropy for the system. Okay. I just put that up there for general interest. Right? Clausius introduced the term entropy and the symbol, but Boltzmann developed the equation that described how you would calculate entropy. And it's not a very useful equation for us because we don't know many of the factors, right? The Boltzmann constant, okay, we know that. Natural log of W, number of possible microstates available, right? How are you going to calculate the number of microstates for a gas that has a mole in it and it's a volume of, say, 100 liters, right? You probably couldn't even do that with a supercomputer. So it's a hypothetical equation, and to calculate the absolute entropy is difficult, if not impossible. So we're not going to worry about it, and you don't have to know that either. Okay, predict the sign delta S for each of the following, and explain increasing entropy. Oh, and explain it. where increasing entropy is positive. So if delta S is positive, entropy is increasing, right? So we have to think of it in terms of system and surroundings too. And for these examples, they are essentially the system. So we want to say what happens to the system in terms of its entropy. Evaporation of alcohol. So if alcohol goes from a liquid to a gas, what's happening to its entropy? Its entropy, its positional entropy is increasing. Its energy entropy is also increasing. So delta S in this case is positive. All right. How about freezing water? Freezing water goes from liquid to solid. And the delta S then is negative. It's decreasing, less than zero. Okay. If you compress an ideal gas at constant temperature, well, if you compress the gas, then as you reduce its available number of microstates, its positional entropy is less than zero. Well, if it's at constant temperature, then the energy entropy is equal to zero. So we're saying that the positional entropy decreases. So that should be negative. If you heat an ideal gas at constant pressure, what's it going to do? If it stays constant pressure, we know that heating it is going to expand it, right? That's Charles' law. If we increase the temperature, and the volume increases, well, we could say that the temperature is constant if we add heat. So this could be greater than zero. This could be greater than zero. But positional entropy is definitely greater than zero. Okay. If we dissolve sodium chloride in water, so what's happening? Well, sodium chloride is a solid to begin with very low entropy by comparison. If we put it in water, those ions separate, and now they have all that volume, that space for those ions, right? We're increasing their positional entropy. So that one should be greater than zero. Okay. All right. All right. There are laws of thermodynamics, like any of our sciences. They have laws to govern. We remember the gas laws, right? Thermodynamics has laws also. The first law of thermodynamics simply says total energy in the universe is constant. In other words, in any process, if you take the entire universe into account, the total energy does not change. Now, if we isolate a system and surroundings, then yeah, that energy value can change within that isolated system and surroundings. But the first law says that for the universe, that doesn't change. The second law introduces the concept of entropy. So any spontaneous process in the universe is always accompanied by an increase in entropy. So the second law says that change in entropy for the universe, for any process, is always greater than zero. So another way of putting that is the universe is running downhill, Right. It's becoming more random as it proceeds. Now there are pockets of organization, right? And we can describe those as stars, planets, um, galaxies, things like that. But for the entire universe, delta S is always greater than zero. Now, your textbook is going to use universe to mean the universe, and it's also going to uh, say an isolated system and surroundings, right? So what I propose is that this is the universe, but this would be total. So what I mean by that is the change in entropy for an isolated system and surroundings is in terms of total entropy. And that value can be positive or negative. Okay, we've covered that already. There's the first law. Total energy of the universe is constant, but the entropy is always increasing. So what we can say, if we take this literally to be the universe, well, actually, let's not do that. Let's say total, delta S total for this system and surroundings is equal to the sum of the system plus entropy of the surroundings. Okay. There's a better expression. If we're only talking about the system and surroundings isolated from the rest of the universe, then delta S total is a better expression of what's happening in here. All right. If we can calculate delta S total for this isolated system and surroundings, and if delta S total is greater than zero, we have a spontaneous process. If, on the other hand, we calculate the total and it's less than zero, it's non-spontaneous. In the forward direction, right? Which automatically means in the reverse direction, it is spontaneous. If delta S total, last but not least, is equal to zero, we are at equilibrium. Okay. All right. So let's say for this process where we have some substance A in the liquid state we're saying that it could potentially be in equilibrium with that same substance as a solid. Which direction involves an increase in energy randomness? Well, the energy randomness would be from right to left, right? Because you have to add energy to the solid to make it a liquid. An increase in potential energy, positional energy, excuse me, would be from right to left. If we're talking about the system, now if we're talking about surroundings, then you have to flip that the other direction. The process is exothermic. That is, energy randomness favors the formation of the solid, going from liquid to solid. The process is exothermic. So which one is favored? Well, if energy can leave the system, then we're favoring the formation of the solid. and a decrease in randomness. That is positional randomness. I just mentioned that one. We reduce the number of microstates available. So we have to ask ourselves, in terms of the balance between the two, which one wins? Okay. So what happens as temperature either... Okay, somebody popped out and back in. That's okay. As temperature increases or decreases, which takes precedence? Well, as temperature increases, positional randomness dominates. Right? Because we're going from... Oh, there's Ann. Zoom. Okay. Positional randomness dominates as temperature increases.
153. I'm gonna go get the dogs in the car.
Got to mute. Mute. Okay, I'll mute you. There you go. As temperature increases, positional randomness dominates. At high temperature, positional randomness dominates. The release of energy becomes less important. Here's what we're saying. And I like to use this analogy. The difference between a college instructor and a billionaire. Let's see, is it A-I-R-E? Billionaire. Right? So a billionaire has lots of money, high temperature, lots of money, which is, we're saying is roughly equivalent to high temperature. Where in this case, large amounts. College instructor has small amounts of dollars. That's roughly equivalent to low temperature. Okay? So that being said, on a percentage basis, if someone were to give $10, let's say $1,000. $1,000 to the billionaire. What difference would that make? Wouldn't make any difference, right? At high temperature, let me finish our statements here. Hold on. Okay. As temperature, okay, at high temperature, if you add heat to the system, then it's like giving a billionaire $1,000. Doesn't make any difference. If you give $1,000 to a college instructor, it makes a huge difference. So randomness or entropy makes a bigger difference to the low temperature situation than it does to the high temperature situation. So as temperature increases from this side to that side, positional randomness dominates rather than energy. This is in terms of energy entropy. Let's see. Let's do it this way. Increasing temperature increased temperature energy entropy is much less important than positional entropy. Okay, let me see if I can explain that again. As we increase the temperature, then any additional addition of temperature makes very little difference to the change in energy entropy, right? On a percentage basis. It's like giving $1,000 to a billionaire. But as we increase temperature, we produce the change in position becomes more important than the temperature does, than the energy does. So to sum it all up, at high temperature, positional randomness dominates. And the change in energy becomes less important. As temperature decreases, then energy randomness is favored and positional randomness becomes less important. So as we decrease the temperature, it's like giving $1,000 to a college instructor. That makes a huge amount of difference. And that $1,000 is analogous to energy, adding energy to the system. At low temperature, it makes a huge difference. Okay, so at what temperature is there a balance between energy randomness and positional randomness? That occurs at equilibrium, right? At equilibrium, you have a balance between positional entropy and energy entropy. And that's going to occur for physical processes. That will occur at phase changes. That's when you have a balance between the two. Okay. Let's see if we can look at these different possible changes and describe them in terms of spontaneous, non-spontaneous, or we just can't tell. Okay. Let's see. I better erase this and make room. Okay. So, if we're talking about a chemical reaction that is exothermic, let's see, exothermic, okay, that's where Q is negative, okay, and we get greater positional randomness. So increase positional randomness. This would be what? This would be a decrease. This would be a decrease in energy randomness. Okay. So we decrease exothermic reaction, decreases the energy randomness, and we're saying that the positional randomness increases. Okay, what can we say about that? We're saying that it's spontaneous. The driving forces are favorable. Well, that doesn't make any sense. Unless we consider the energy randomness of the surroundings. Right? If we say that, that means we increase delta S energy for surroundings. In that case, both of them are positive. So when energy leaves the system and goes into the surroundings, we're saying that that's a spontaneous process because it increases the energy randomness of the surroundings. And then this is obvious, where we increase the positional randomness, then we get both are spontaneous, and add them together, you get a spontaneous reaction. If it's exothermic but becomes less positional random, if now we say this is still the case, but instead we decrease, for the system, okay, now we really can't tell because one is favorable and the other is not. Positional randomness is not favorable, but energy randomness is favorable. So exothermic means favorable. In terms of randomness, and when I say that, I mean randomness of energy randomness of the surroundings. Okay. If we do the other way, right, we just flip them and we say an endothermic reaction. Now the endothermic reaction is delta S for the more positionally random. So this is positional for the system is greater than 0, but the delta S energy for the surroundings is less than 0 because the system is drawing energy from its surroundings. Okay, again, we can't tell because one is favorable and the other is not. But if we have an endothermic process where the system becomes less positionally random, then we say it's non-spontaneous. Under those conditions, we can definitely say that the process is non-spontaneous. And A and D are not affected by temperature. Let's see, how does that work? A, exothermic. I'm not sure about that one. We're saying that the middle ones, where you cannot tell, they're dependent on temperature. Well, yeah, because it's that situation where we have high temperature versus low temperature. Right. High temperature is going to be positionally favor positional, and low temperature is going to favor energy. So that does make a difference with B and C, whereas A and D they're either spontaneous or non-spontaneous regardless of the temperature. Okay, that's a little hard to grasp. I grant you that. So what we need to do is discuss this eventually in terms of free energy. And I'll introduce that topic in just a minute. The delta S of the surroundings depends on the direction of heat flow primarily. So as heat leaves the system, randomness in the surroundings increases. And this is total randomness, but primarily from energy transfer. So exothermic, where delta H is negative or Q is negative, we get an increase in energy randomness for the surroundings. As heat enters the system, then randomness in the surroundings decreases. Okay, we're headed somewhere with this. The magnitude of that delta S for the surroundings depends on the temperature change. And the initial condition. Right? The change in entropy has a greater effect on the surroundings when it starts at a low entropy than if it starts at a greater entropy. So if we have a low energy entropy for the surroundings and we have an exothermic process, then it's on a percentage basis, the change in surroundings entropy is much greater than it is at a higher temperature. So, to sum it all up, the delta S for the surroundings is proportional to the heat transferred. Okay? We're not making equivalence yet. It's proportional to the heat transferred, but inversely proportional to the temperature. Okay? That just says the delta S for the surroundings increases as the amount of heat transferred to the surroundings occurs, but it's inversely proportional to the temperature. So as the temperature gets greater, delta S gets smaller. And here's what that looks like in a formula right here. Well, let's see. I shouldn't have skipped those slides. This driving force is provided by energy flow, that is heat. And the magnitude of the entropy change is equal to the quantity of heat divided by the quantity of temperature. And this temperature must be in K. It has to be in units of K because we cannot tolerate a negative sign. We have to use the absolute temperature. All right. So here's what we're saying. Right? It's equal to those, except there's the fly in the ointment is if this is exothermic, it's going to be negative. And temperature doesn't have a sign. So overall, this would be negative. Right? And if we're saying as we increase the value of Q and decrease T, we get a more spontaneous reaction, then this has to be positive. So based upon our convention, what we have to do is fudge. We just put a negative sign there, and that solves the problem. And sometimes you'll see it substituted the Q, we'll substitute delta H. Now, with one caveat, Q is not the same as delta H, but the values are equal in one certain condition, and we'll talk about that in just a second. Okay, when is delta H equal to Q? Delta H is enthalpy. It's known as a potential for energy transfer, where Q is a measured quantity of heat movement from one location to another. In addition, enthalpy, delta H, is a state function. We don't care how it got there. Whereas Q is a path function. Depending on what path it takes, Q will be different. If you go from this state of enthalpy to this state of enthalpy, and you go straight, you'll get a Q value. But if you go this way, you get a different Q value. Now, remember, we threw up this equation. Delta H equals internal energy plus P delta V. Well, actually, the beginning situation is simply a change in pressure volume. We modified it already, but I want to show you how that modification came to be. If we insert the equivalence of delta E is Q plus W. Right? So now we have delta H equals Q plus W, right, from here, plus delta PV. Okay. If the process takes place at constant pressure, then we can move the pressure term outside of the parentheses. I'll put it out here. So if it's at constant pressure, then pressure doesn't change, only volume changes. And we still have Q plus W. Okay. We also know that work is pressure against a change in volume. This is for gases. If we have a movable piston and we try to, and the system is inside the piston, then if we push down on it, we're applying a force or a pressure. And if that pressure is constant, then it will go down to a certain point and change the volume. So work is equal to a negative pressure times a change in volume. Because in this scenario, our pressure is constant. And remember, we have to introduce that negative sign in order to maintain the convention. Where work on a system has to be positive. And if we apply pressure, but the volume is decreasing, right? Final minus initial is a negative value, then that would give us a negative work, but we've done work on the system, so it has to be positive. That's why we introduce the negative. Okay. So with this term, then if we say this term right here is negative P delta V, but this is P delta V positive Q delta H, then this one cancels that one. What we're saying is that under conditions of constant pressure, enthalpy is equal to the measured heat transfer. So while delta H and Q, are expressions of different things, that numerically they're equal if the process is carried out under constant pressure. You can let the volume change, but the pressure cannot change in order for delta H equal to Q. All right. Now let's clear the board again. Yeah, we'll clear all of this. All right. So under, remember we said that delta S total equals delta S for the system plus delta S for the surroundings. If the change in entropy for the system and the change in entropy for the surroundings, and this can occur because we know that it could be energy entropy, it could be positional entropy, so that the mix of those two will give you the surroundings entropy and the system entropy. When you add those together, if they're both positive, then this one must be positive, and that is a spontaneous process. Okay? If they're both negative, though, then this can only be negative, and this is non-spontaneous. Okay? If the entropy change for the system is positive, but the entropy change for the surroundings is negative, then it depends on which one's larger. If this one is greater than that one, if that one's greater than that one, then we have a positive. But if this one is less than that one, we have a negative. Okay. And similarly, if we have a negative here and a positive here, then if this one is greater than that one, if system is greater than surroundings is greater than system, then we will have a positive. But if surroundings is less than system, we'll have a negative. Okay. All right. Now for an easier way to assess whether a reaction is spontaneous or not. And that comes from a physical chemist by the name of Josiah Gibbs. Now, I'll emphasize that Gibbs was not the only person working on thermodynamics at the time. And there were several other scientists who proposed a similar approach to assessing the energy balance and entropy of a given reaction. But the work that Gibbs did and produced and published in terms of his equation is the one that is dominant. Now, if you're going to be a chemistry major, particularly if you're going to be a physical chemist, then you're going to learn all of those others and have to know when each one is applicable to the greatest degree for a given reaction. But for our purposes, we're going to focus on Gibbs' free energy equation. And Gibbs' approach was to ask the question, how much of this enthalpy, how much of this energy potential from a reaction is available to do useful work? Okay. And he came up with this equation. Okay. That much energy, the change that gives you this amount of energy, is available for useful work, maximum available for useful work. And it's based upon what's the enthalpy of the reaction, and then minus this loss. This is considered a loss. That's why it's a negative. This is lost from entropy to give you this free energy. The Gibbs free energy is equivalent to the maximum work that can be obtained from any process. Now, by convention, if there are no subscripts, then we automatically assume system. System, system, system. That's if there are no subscripts. If there are subscripts, then they'll tell you whether it's surroundings or not. So we can modify this equation, divide through the whole equation by negative t. So if we divide the whole thing through by negative t into this one gives you negative delta G over T is equal to negative delta H over T. And then the negative T cancels the negative T here, and that's plus delta S. Okay? Remember our previous equation where we said delta S equals negative delta H over T. Right? So there you have this term is that term, and this is surroundings. So if we substitute this term over here, delta S surroundings, and to be explicit, we'll say delta S system is equal to negative delta G over T. If we add these two together and they are positive, if they're positive, then the process is spontaneous. If they're positive, spontaneous, but delta G would have to be negative to be equal to positive. In other words, if this were a negative term times that negative, then we get a positive. So what we're saying is spontaneous is implied by a negative delta G. If the free energy is negative, then the process is spontaneous. Okay? So delta S total equals negative delta G over T. All right. So I'm going to leave that one up there. I'm going to put this one up there for a future reference if we need it. And negative delta G over T equals delta S total. Okay. All right. Okay. A liquid is vaporized at its boiling point. Constant pressure. Predict the signs of each one of these. Well, where do we go first? If it's under constant pressure, then the volume must increase, right? So as the gas in this piston under constant pressure, and we go liquid is vaporized at its boiling point. So we get this liquid and we make a gas out of it. Then it's going to, against that pressure, volume is going to increase. Okay? So a force is being applied against the surroundings to increase the volume. So work is leaving the system. That makes it negative. So W is negative. Okay? How about Q? Well, at the boiling point, we need heat. Heat must be applied in order to change that liquid to a gas. So that means we have to add heat. Heat must be added to the system. That makes it positive. Okay? How about delta H? Constant pressure means that delta H is the same as Q. So it must also be positive. In fact, it'll be exactly the same value too. How about delta S for the system? The gas is more disordered than the liquid, right? So delta S for the system is positive. There we go. How about surroundings? The delta S for the surroundings. As heat enters the system, the surroundings become more ordered in terms of energy in particular, right? Energy entropy for the surroundings decreases. Okay? It's negative. Okay. How about delta G? At the boiling point, the system is at equilibrium, which means delta G is 0. Delta G is 0. So, delta H, right. If this equation, Gibbs equation, is correct, and this is 0, right? That's at equilibrium. At equilibrium, then delta H equals T delta S. And again, this is for the system. Okay, that's what we're talking about, system. Delta H equals T times the change in entropy. Delta H equals the temperature times the change in entropy. And the entropy for the system is positive. So delta H would also be positive. Okay. So let's take this example. See, we don't need these anymore. The value of delta H of vaporization, that is, how much heat for a mole of liquid does it take to convert that liquid to the vapor? So we're saying we're given delta H of vaporization is equal to 45.7 kilojoules. 45.7 kilojoules per mole. Okay. And this is at its normal boiling point of 72.5 degrees. Temperature, boiling point, 72.5 degrees C. Okay. Calculate delta S system, delta S surroundings, and delta G for the vaporization of 1 mole of this substance at 1 atmosphere. Okay. At the boiling point, we have equilibrium. So delta G is 0. Right? Because at the boiling point, delta G is 0. Okay. Delta S for the surroundings, we have here negative delta H over T. So what's delta H? It's needs to be in joules, right? Because these are standardized values. So it can't be kilojoules. It needs to be negative, just 45.7 times 10 to the third joules per mole. And then the temperature has to be 72.5 plus 273. That's K. Okay. And when we divide that, we get a negative value. Delta S for the surroundings is a negative 132 joules per K mole. Notice the units. For delta S, joules per K mole. Joules per K mole. This is in the denominator. Okay, that's the delta S for the surroundings. Well, oh, I left out one of the formulas. At equilibrium, delta S total has to be 0. Right? We don't have any change in disorder at equilibrium. So if that's the case, then delta S for the system is just the reverse sign, plus 132 joule per mole. Okay. Now, if the system's not at equilibrium, we have a different scenario. Do we have time for Professor Dave? I think we do. I'm going to let him talk.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around. Entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T. So entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash nonpolar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long nonpolar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the nonpolar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water soluble due to the polar heads facing out. That's how soap works, and that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy storing processes. In this way, systems can defy entropy on the small scale. But the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. Professor Dave put Gibbs free energy equation up on the board and showed you what would happen if the enthalpy were positive or negative as compared to the positive or negative entropy. And if the entropy is positive and the enthalpy is negative, then delta G is always negative. So it's spontaneous at any temperature. But the last one in that list, if the entropy is negative and the enthalpy is positive, then delta H is always positive and non-spontaneous at any temperature. The variability comes in where you have entropy is positive, enthalpy is also positive, and under that situation, since entropy is positive, the process is likely to be spontaneous, a negative free energy, only at high temperatures, or best as the temperature increases. Whereas if the entropy is negative and the enthalpy is also negative, then that process will give you a negative free energy or a spontaneous process predominantly when the temperature is low. Okay. This one, yes, okay. Gas A2, which is a diatomic gas with an A element, reacts with gas B2. Okay. We have this one reacting with this one, and what does it produce? To form gas AB at constant temperature and pressure. So in order to balance, we need two ABs on that side, right? The bond energy of AB is much greater than that of either of these reactions. So let's see, bond energy is greater here for A or B. This is a stronger bond. Okay. What does that mean? Well, in terms of the chemistry, it takes less energy to break this bond or that bond than it does to break this bond. All right. All right. With that in mind, we want to predict the signs of delta H and then the others, S, 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 and this one's surroundings. This one is system, and this one's total. Okay. So we'll go to the next slide. And we can use this equation, right? Remember, delta H, where we have the bonds that are broken, we put in the values for the bonds that are broken and subtract the bonds that are formed, and we get a delta H, right? So if we do that, the energy to break the bonds for the reactants is greater than the energy to break the bonds for the products. That is, if this has a stronger bond, that means it's at lower energy. And where did that energy go? There was more energy in these bonds because they're easier to break. So they're at higher energy. Okay, that means we have some energy left over here. We have a delta H left over, right? Exothermic reaction. And that gives you a negative sign. Right? By convention, if heat is leaving the system, it's negative. All right. If we know that delta H for the surroundings is negative, well, delta H for the system would be the opposite, right? If heat is leaving the system, then it must be positive. It must be added to the surroundings, which means if we're predicting delta S for the surroundings, then delta H must be, well, delta H is negative, and then a negative negative is a positive. So the delta S for the surroundings must increase. Okay. Now we're not sure about the system, you know, whether it's, we can't tell for sure, but we're saying that the delta S for the system is approximately 0. Okay. If that's the case, then the delta S for total is also going to be positive. And that would make the reaction spontaneous. Okay. We'll just throw in the third law of thermodynamics to be complete. the entropy of a perfect crystal at 0 K is 0. If we had a perfect crystalline structure and our temperature is 0 K, then the entropy for that crystal would be 0. What that means is that anything above 0 K has an entropy value. That means that all entropy values for individual components, atoms, molecules, whatever, they must be positive, right? Remember, we can have delta H's for that are positive or negative, but by convention, the delta H for any substance, any element under standard conditions of temperature and pressure is 0. This is for elements, right? So we can have a negative delta H or a positive delta H for any given compound. All right. Remember that little 0. This one means standard conditions of temperature and pressure. So the standard temperature is 25 degrees Celsius for anything except gases. So our standard is 25 degrees Celsius or 298 K and 1 atmosphere pressure. So under standard conditions, we can apply a similar calculation, a similar formula to calculating the enthalpy for a reaction. All we need is the enthalpy for each of the products minus the enthalpy for all the reactants combined. And we can do the same thing for entropy. So the entropy under standard conditions is equal to the entropy for all of the products minus the entropy for all of the reactants. And that way, it makes calculation much easier. We can also say that the standard entropy generally increases as the complexity of the molecule increases. So larger molecules are going to have higher entropy than smaller molecules. And this illustration opposes water versus hydrogen. So water has 3 atoms, hydrogen only has 2. So what are the possible energy and positional entropies that we can see from water? Well, we can have that symmetric stretch of the oxygen-hydrogen bonds. We can have the scissors, or we can have an asymmetrical stretch, or we can have rotation. Those 4 possibilities. There are other modes of movement, but those illustrate our point. If we go to diatomic hydrogen, though, it can only stretch and rotate. So that means that water has more possible microstates than hydrogen. And at the same condition of temperature and pressure, standard conditions, water will have a higher entropy than hydrogen gas. Now, if we want to calculate the standard entropy change for this reaction, remember when we were doing enthalpies, the sodium and hydrogen would be 0. So we wouldn't even have to look at those. But in this case, since entropy is characteristic of all molecules, all atoms, as long as they're above 0 K and not part of a perfect crystal, then they all have values. So we would say, all right, 2 sodium hydroxides, 2 times 50. I'm going to leave out the units for convenience. And we're calculating the change in entropy, the standard change of entropy for this reaction. So this is products, and then hydrogen is only one hydrogen, so it's 131, excuse me. And then subtract reactants. So 2 sodiums is 2 times 51 plus 2 waters, 2 times 70. Okay. So this is 100 plus it's 231. And this is 102, and this is 140. So that's 242 minus. Okay. And then that value would be delta S for this reaction under standard conditions is equal to 4 minus 11 joules per K. Why didn't I put moles in there? Because we canceled out moles here. This is 2 moles, this is 1 mole, 2 moles, 2 moles. The moles cancel. So all we have left is joules per K. Okay. So that means that the when this reaction proceeds, it should become more ordered. Now, there are numerous ways to approach this to illustrate the fact that the reaction increases or decreases entropy, decreases entropy. If we look, the reactants have 2 moles each, 2 sodiums, 2 waters. And the products have 2 plus 1 is 3. So we went from 4 to 3. And that's one way of rationalizing the fact that this value is negative. The overall entropy decreased. Okay. We can do the same thing for Gibbs free energy equation under standard conditions, right? Which will be delta G0 equals delta H0 minus T delta S0 under standard conditions. And we can do the calculations just like we did before. Free energy of products minus free energy of reactants gives us the overall free energy. And the nice thing about that is, if you make this calculation, then you can say, under standard conditions, this is a spontaneous reaction or this is not a spontaneous reaction, just based upon the sign of delta G. All right. Let's see if we can make sense of this one. A stable diatomic molecule spontaneously forms from its atoms. So this diatomic molecule, spontaneously forms from its atoms. Okay? What's the sign of each one of these? Well, these separate atoms, when they come together, they're going to give off energy because they form a bond. So delta H should be negative. It should be exothermic. All right. Oops. I didn't realize the animation gave you all the answers. All right. Delta S and delta G. If we can determine what delta S is, then we should be able to, under standard conditions, tell what delta G is. Well, delta S is a measure of order, disorder, or number of microstates. We have fewer microstates here than we do here. So the order is increasing. The disorder is decreasing. Okay? So if this is negative, and this is negative, both are negative, then how do we know that this one is negative? Well, it's given to us in the problem. The problem says spontaneous. So this one has to be negative. So what that's telling us is that this value times that value is much smaller than this value. Right? This is smaller than that value because this is positive now, negative times negative, positive, and this is negative, then it gives us a negative here. That means that this total must be less than that one. Okay. All right. So let's look at another problem. Consider this following system. At 25 degrees, so standard temperature, phosphorus trichloride gas plus chlorine gas equals phosphorus pentachloride gas. And we're given that the delta G standard conditions equals negative 92.50, kilojoules. Okay, what will happen to the ratio of the partial pressures of PCl5 to partial pressures of PCl3 if the temperature is raised? Excuse me. If we increase the temperature, the question is the ratio of PCl5 to PCl3. Let's see, pressure of PCl5 to PCl3. What happens to that? Does it go up or down? All right. If we take Gibbs free energy equation, we know that delta G is minus 92.5 kilojoules. Let's see. I thought I'd get an explanation from that, but I guess I don't. Okay, there's the explanation on the bottom. Delta S is negative. How do we know that? Well, we're going from 2 moles to 1 mole, right? So we're looking at this one as negative because we're going from a more ordered 2 moles to 1 mole. Okay, this is negative or spontaneous. So what does that mean for delta H? Well, this is 25 degrees, or it's a positive number. So this is overall negative. Right? Overall positive. Because negative times negative is positive. And this is negative, so that means this one must be negative or exothermic. Okay? Everybody follow me there? Because this is negative, and negative is positive, but this is negative from here, then delta H must be negative in order to give you a negative here. Okay, if we know that that's negative, that means that the delta H is on this side. Okay, it's exothermic. Now what happens? Use Le Chatelier. What happens if we increase the temperature? If we increase the temperature, we're going to drive the reaction back this way. We're going to increase this one and decrease that one. So the ratio will decrease. Make the denominator bigger, the numerator smaller, we get a smaller ratio. That's the logic behind this problem solution. All right. One thing we do know is that most chemical reactions, ones that we're interested in, don't occur under standard conditions. So in order to predict whether it's spontaneous, we need a way to calculate delta G under the given conditions, and especially if we know under standard conditions, how can we relate standard conditions to current conditions, right? And here's one way. If we know the pressure and we know the temperature and we know R, which is our gas constant, then we can calculate delta G from the standard delta G and those other factors. We can also know that actual delta G if we know what the Q is. In other words, the reaction is not in equilibrium. So we can calculate the Q. Then we can take the natural log of the Q times R times Kelvin temperature plus delta G0, and that will give us delta G. And here we're using R is joules per K mole, 8.3145. Let's see if we got an example here. All right. Yeah, we're going to do an example in just a minute. And there are sample problems in the review documents. And today I've handed out version 1 and version 2 of review documents. There's some overlap between the two, but I gave you both of them because I noticed that when I do my review, I pick problems from both of them. So I want to give you both copies. Okay, now, so what does delta G mean for a chemical reaction? Chemical reactions, we've learned up to this point, tend toward the lowest possible energy. And that is an equilibrium state. Equilibrium means that they don't go to completion. Now, for chemical reactions, we know this is true. So if we see on the right-hand side, that ball rolls from A, and it doesn't quite get to B. It stops at C, which means that it's an equilibrium. We have some A left over, we have some B left over, and at our position C, we've got this exchange that's going on for chemical equilibrium. On the other hand, if we're talking about a phase change occurs under circumstances where you go all the way from liquid to gas, or liquid to solid, or solid to liquid, or solid to gas. Those phase changes occur analogous to this ball rolling down from A to B, completion, all the way to the end. Okay, so if we're talking about equilibrium then, we're talking about a system that has an established equilibrium constant, or K value. Remember our K, if we have A, B, C, and D in equilibrium, then our K value for this equation would be C and D over A and B to their powers. That's our equilibrium, our mass action equation. Then we know that under those circumstances, if we're at equilibrium, we know that delta G is going to be 0, right? But under standard conditions, we will still have a delta G value, right? Because delta G under standard conditions isn't at equilibrium. But if we have delta G equal equilibrium, then we have that's equal to delta G 0, which is an add RT, excuse me, RT log before it was Q, right? If we were not at equilibrium. But now that we're at equilibrium, we're not calculating Q anymore, we're calculating K. So at equilibrium, this expression is equal to 0, which means what? It means that delta G0 equals negative RT log K. All right? What does that tell us? That means if we have a system at equilibrium and we measure the K value, we calculate the K at a given temperature, we can determine the standard free energy for that equation. Or if we know the standard free energy for an equation, we can calculate the K for any given temperature. All right. Now, these next two slides can really spin your head around. So let me take this slow. What we're trying to do here, remember that previous slide where we had the ball running from A and not going to B, but ending up at C in the middle. Okay, so think of it in those terms. We have free energy here on the y-axis, and we have the fraction of A on the x-axis. And we're looking at a transition from this gas to this gas. Okay? And we've implied from that value, I mean that double barbed arrow, that the system can be at equilibrium some point. All right? So the fraction of A on the x-axis, we go from 0 to 1, fraction, actually, we'll use the terminology we used before. The mole fraction of A is increasing in this direction. What does that mean for B? That means the mole fraction of B is increasing from right to left. Okay? So we know with A and B, the mole fraction is going to be a total of 1. That means if we have 0.5 mole fraction for A, 0.5 mole fraction for B. Okay, now that I've laid the groundwork, how do we calculate G for each one of these? Well, the free energy for A is in terms of G. The free energy for A is in terms of its standard free energy plus RT times log partial pressure of A. So as the partial pressure of A decreases during the reaction, this is going to decrease as well. Okay? As A decreases, partial pressure decreases, and G also decreases based upon that formula. Consequently, as we increase B, it's going to be, on this side, it's going to, as we, let's see, as we increase the mole fraction, the free energy then, the free energy of B versus A, the free energy of B is going to decrease as it increases. Because the partial pressure of B is decreasing. Let's see. Fraction of A reacted. Yeah, fraction of A reacted, fraction of B reacted. That's right. So we're going to reach a point where the free energy is at a minimum at this point, C, and that's equilibrium, where you have a minimum value of free energy. Another way of putting that is, as A disappears, the free energy of A decreases since its partial pressure decreases. And as B appears, the free energy of B increases since partial pressure of B increases. As long as the free energy of A is greater than B, then the reaction will proceed to the right. But when the free energy of B equals the free energy of A, then the total is the two put together, and one is positive, the other is negative, and you get a change in free energy of 0. That's equilibrium. Previously, we just told you at equilibrium, delta G is 0. This is an attempt to explain why that is. Okay. So let's take a look at that equation. I don't think I wrote that one up here, did I? No, I didn't. Let's see. Delta G 0 equals minus RT log K. So what we notice is at equilibrium, delta G is 0 and K equals 1. If delta G is 0 here, then what does that mean for this expression? Well, if delta G, if delta G 0 equals 0, then that's equal to minus RT log K. And this is a non-zero number, 8.3145. This is a non-zero number. This is greater than 0. So these two greater than 0 gives you a negative here. How do you get 0 out of non-zero numbers times this expression? The only way you can do that is to say this is the power of whatever the power of E is equals K. Excuse me. Let's see. Log base E of K equals some number, right? So it's E to this number equals K. Oh, this has to be 0. Yeah, that has to be 0. This is 0. So E to the 0 power equals 1. Okay, I lost myself for a second. We know that this whole thing has to be 0, so that has to be 0. And if this has to be 0, then E to the 0 equals K, and that's 1. Any number to the 0 power is 1. Okay, that's why delta G 0 equals 0 and K equals 1. Well, if delta G is less than 0, if delta G is, say, negative 1, right, then the only way to get that, let's just say this is less than 0. The only way to get to be less than 0 is for K to be greater than 1. Because we've already established where 0 is, then K has to be greater than 1 to give us a value that's still negative. Right? K has to be greater than 1 to give this a positive times a negative makes a negative. And consequently, if delta G is greater than 0, then in order to give us greater than 0, this has to be negative. This has to be, negative. Less than 1 makes this negative times negative makes that a positive. Okay. So they're inversely proportional, so to speak. If delta G0 is 0, then K has to be 1. If delta G0 is less than 0 or spontaneous, then K is greater than 1. And delta G0 is greater than 0, then K has to be less than 1. And we know from experience that when K is greater than 1, we have a predominance of product. K is less than 1, we have a predominance of reactants. Okay. Now, I'm over time. So if you have to go, go, and I'll keep recording until we're finished. We're not too far from the end, actually. 1, 2, 3. I got 4 more slides. So go back to Gibbs' original objective. How much of enthalpy, how much of the potential energy from a reaction can be used to do useful work? That's where this expression comes in. Maximum possible work is equal to a change in G. So if this is negative, then this is negative, which means the system is doing work on the surroundings, and that's what we want. Work on the surroundings means we're extracting work from the system. So we don't have to change the signs here. If this is negative, spontaneous, then this will also be negative, and that energy will be available to do work. Now that's the maximum. The only time you can get maximum work out of a process is if a process is reversible. Right? And that only occurs theoretically when you get the very, very smallest, infinitesimally small changes. Right? And that's theoretical. That never happens. All natural processes are irreversible. So what that means is maximum work can never be extracted from the available free energy. There are always losses. Okay. What we're saying here in this discussion of the temperature dependence of K is if we say that the equilibrium point occurs at the lowest value of free energy available to the system. And we saw that in that curve. The lowest possible free energy is where equilibrium occurs. In that case, delta G is 0, and we equated that to delta G 0 plus RT log K. So we continue to solve the equation, and we get to the point where we have delta G is equal to minus RT log K is also equal to delta H minus T delta S. That's the Gibbs free energy equation. Then we divide the whole equation through by negative RT, and we get this equation. Right? We get log K equals negative standard enthalpy divided by R times 1 over T plus delta S 0 over R. Now, what does that look like? That looks like Y equals MX plus B. That is a straight line. So what would you plot for this reaction? If you measured the K at different temperatures, and that's K degrees, not K EQ. This is K EQ. And you plot these two together, and I think that's on the next slide. We have an example. Yep. Then you get values that give you a straight line. Okay. Now, I think this line, in this case, the line is negative slope, but it could possibly be a positive slope. If delta H is positive, then we could get a positive slope, right? If it were endothermic, then, exothermic gives us a positive slope. Endothermic gives us a negative slope. So this is an endothermic reaction because of its negative slope. This equation has a name, I think. I can't remember what the name is. I think it's Clausius-Clapeyron equation. But if you have a line like this, and you follow that best fit line to here, that value is delta S0 over R. And if you have a slope, the slope is equal to negative delta H0 over R. Okay, so you can deduce from this both the delta S under standard conditions and the delta H under standard conditions. Now let's see. Yes, they have to be under standard conditions. They have to be under equilibrium conditions where delta G is 0. So when delta G is 0, then we can plot under equilibrium conditions, we can plot this graph and determine those values. Okay. Last slide. Any real pathway always wastes energy. We can never get to maximum work or the Gibbs free energy. We can never reach that in reality. All real processes are irreversible. Okay, this is another way of defining the 3 laws of thermodynamics. The first law says you can't win. You can only break even. In other words, you can't get more energy out of a system than you put in. In other words, there's always conservation of energy. That's what the first law is. You can't win, you can just break even. Second law says you can't even break even. Any transfer of energy will result in the waste of energy unless a temperature of absolute 0 can be achieved. If the surroundings are at absolute 0, then you can transfer energy with no losses. But that never happens either. Third law says you can't get out of the game. In other words, you can never achieve absolute 0. And that should be the last slide. Well, oh yeah, the moral of this story is whenever we use energy, we degrade its usefulness. The only way to get the maximum energy from a process is to couple it with absolute 0. And that never happens. But even if you did get to absolute 0, then it would be worthless. You couldn't use it anymore. Right? There has to be a difference, an energy difference between the system and the surroundings in order to extract energy. So that's why our automobile engines run at thousands of degrees inside the cylinder, and the energy from there is dumped into room temperature. That difference in temperature is what allows your automobile motor to operate. They're called heat engines. And that's an entire semester of discussion if you ever get to that point or want to. Okay, we're done. So we're going to, next time we meet on Thursday, we'll do a review of this material, and then we'll go in the lab and do the Ka of acetic acid. So have your notebooks prepared for inspection, and then we'll do the titrations using a pH meter. So we're going to draw a curve, a titration curve, and there's a video discussion of it in Brightspace. I encourage you to look at that, and that'll give you a feel for why this titration works and how to extract the K value from it. I don't believe, let me see. Let me see if there are any lab questions in the document. Yeah, there are. There are discussion and pre-lab questions. And post-lab questions. Okay. And the introductory video for this lab will fill in some of those blanks with questions. Certainly the pre-lab and discussion questions.